and welcome to lecture number 3 of electronic devices and circuits. Today we'll be studying about diffusion current, drift current, Fermi level, Fermi energy, then we'll be doing up some questions. So let's get started. Let's start with diffusion current. Now what does diffusion means? Well, diffusion means the migration of charge carriers from higher concentration to lower concentration, or from higher density to the lower density. Why it is happening? It is happening due to concentration gradient. Since they are just diffusing on their own, can we say that this is a force-free process? Force-free. Whereas in the drift current, what is happening? That we are applying an external electric field which is drifting the charges. So, can I say this is... My triangle looks so bad. This is a forced process. Can you understand the difference? In this, just look at the words. Diffusion. Diffusion means it is going from higher concentration to lower concentration on its own. And why it is happening? It is happening due to the concentration gradient. While in this, they are drifting. And if we want to drift something, we have to apply an external force. So here that external force is the applied electric field. So this one is a forced process, while this one is a force-free process. Are we clear? So now the gradient is given by d by dx. Now what should be the electron concentration gradient? Electron concentration gradient will be simply dN by dx, right? And what should be the hole's concentration gradient? I know you have already written that in your notebook because you all are smart students. This will be simply dP by dx. Now let's have a look at some expressions of diffusion and drift current, and then we'll calculate the total current density. Now diffusion current density due to electrons is given by Q dN by dx. Now this, do you remember this? You must be familiar with this if you have seen the lecture number 1. This was the diffusion constant. We studied about it. The expression for this was dN is equals to mu n into Vt. Do you remember it now? Can you recall it? Similarly, let's write the diffusion current density due to the hole. Now let's write the other expression. So this will be J P diffusion. Try to write it from this expression. Write it in your notebook. This will be Q. This will be dP. This will be small dP by dx. I left a space over here which was intentional because we are about to add a minus sign. Now some smart minds will definitely leave a comment over here that ma'am, why we are adding minus sign when the holes are always taken positive. So let me just cut the whole thing short. Now what happens is that this J, this current density thing, it is given by minus Q d by dx. This is how the expression is. Then for the n type, if I'm considering n, so what I'll do for this Jn, I'll write minus. Then what is the charge on the, what is the charge on the electron? It will be minus q, and then simply the same expression that we wrote above. So this makes the final expression to be positive, right? See, now similarly, what will happen? Look at my arrows. Yes, so similarly, what will happen for Jp? We'll write this, but the charge will be plus q, so which will give us the minus expression. Is that clear now? Well, similarly for this one, if you can recall the diffusion coefficient, this was simply mu p pt, right? Now the drift current density due to the electrons is given by Jn. You have to write in bracket drift so that we don't get confused that what we are writing for. This will be n q mu n into the electric field, right? Similarly, drift current density due to holes will be given by pq mu p into e. Now if I'm saying you that I have to calculate the total current density, then what I should do? I should simply add both of them, right? The drift current and the diffusion current. So I'm saying that it will be drift plus diffusion, right? So let's write the total current due to electrons. What it will be? Jn drift plus Jn diffusion. Now as I'm writing, I want you to write here in the second step, just add both of them and write it over here in your notebook. Similarly, Jp is equals to Jp drift plus Jp diffusion. Now cross check that what you have written in your notebook, is this correct or not? I hope you are able to write these expressions. Yes, we are doing a good progress. We are understanding everything, right? So let's now move on ahead. Now let me write the current density expressions again. Here they are. Now what we can deduce from these expressions is that, can you see the drift current? It depends on, should I write the drift current depends on first the carrier concentration. Second, what it is depending upon? What was this? This was the mobility, right? Third thing, what it is depending upon? The field intensity. Now if any question is coming on this topic, you can always do it, any theoretical question, any numerical, because we know this formula and we derived it ourselves, right? Similarly, for this also, it is depending on the carrier concentration, mobility and field intensity, while the diffusion current, the diffusion current, what it is depending upon? The concentration gradient. We should learn this subject in such a way that we don't have to revise it, because we have to revise other subjects like networks and analog and signal systems. So we will learn it in such a way that we don't have to revise it, or we just have to revise this once and we can recall it as soon as possible. Now I forgot to write the unit, but you know the unit of current density. It is a centimeter square ampere per centimeter square. Now I told you about that in a semiconductor there is an unequal distribution of charge carriers, and due to which the diffusion occurs. So sometimes the diffusion, it is also associated with random motion of charge carriers in semiconductor due to the thermal vibrations. So if we have to write a formula for the length of diffusion, we can write it as L is equals to under root D into tau. Now this is a familiar D. This is diffusion constant. This is our diffusion constant, and this keeps giving its appearance again and again. This is a very important constant. And the second, this thing, it is as usual carrier life time. It is the average carrier lifetime. So if you can write it as mu into Vt into tau, because this was the formula for D. So now the length of the diffusion, it depends on, like we did in the last slide, it depends on the diffusion constant, it depends on the carrier lifetime, it depends on the mobility of the charge carrier, and it depends on the temperature, because the formula for Vt, you remember, it was T upon 11600. This was it. This was the formula for Vt, thermal voltage. Well, that's all you should know about diffusion current and drift current in terms of gate. Now let's move on to uniformly. Well, it cannot be uniformly. This is mistake. The question which came, it was the electron concentration in a sample of non-uniformly doped N-type silicon at 300 degree Kelvin varies from x at x0 μm. What is the concentration? 10 to the power 17 per meter cube, right? At x is equals to 2 μm, what is the concentration? 10 to the power 6 into 10 to the power 16 per meter cube. Now value of Q is given. This is Q. Value of Dn is also given, which is 35. We just have to put the formula. So now one special thing which is mentioned over here is no electric field. So let's first write the formula. So this is the formula which we just studied. Since no electric field is given, can I say that this whole thing will be 0, because this is in multiplication? So this is left. Let's just put the values very fast, right? I have written this. Now this is how you write the gradient, subtracting the higher into lower. Now here what I should write? Right, 2 into 10 to the power minus 4 minus 0. Why I wrote this? Because I converted the mu m into centimeter. We have to keep the units uniform. The whole game over here is of units. So this will give me 1120 ampere per centimeter square. Now let's move on to the next problem. Now this question was asked in 2004 for 2 marks. At a glance it looks like a BJT problem, but if you see here we have the diffusion constant. I told you it's a very important member of EDC. So if you find this, you should already know that this is an EDC problem. So let's do it quickly. So the n is given as 10 to the power 14 per meter cube from here, and the diffusion constant is given here. So they are asking that what is the collector current. Well, the collector current will be simply, here I am writing it as JC, it will be Q dN by dx. If we put the values, this will give me 8 amperes per meter cube. This is the answer. So this question was asked in 2010 for 2 marks, and this is a linked question. First you have to study this and then you have to answer these 2 questions. For the first part, we simply know that the field intensity is given by V by D. So just put the values quickly. 10 to the power minus 6. Okay. This will be the, yes, since the unit here is in centimeter, I can write it like this. So this is the answer. For the second part, now we have to write the formula for drift current density, which is very simple. This was N, Q, mu n and E. So let me just put the values real fast. 10 to the power 16 and what is this? 1.6 into 10 to the minus. You have to be faster than me and you should have ticked the answer right now. Oh no, I'm lagging behind. 1350 and into 10 into 10 to the power 3. Right. So the answer will be 2.16 into 10 to the power 4. So do I have this option? Yes, I have this option. So we are done with this question too. So in linked question, what happens is that the answer of first is generally used in the second. Like here, what we calculated is used here, and then we got the second answer. So if your first answer is wrong, then definitely your second answer gonna be wrong and you'll lose both the questions. So be a little careful while solving the first one. That will be my tip. Now let's move on to the next and the last problem for this lecture. So this question was asked in 2014 for 2 marks, and this is a homework problem because we did similar questions. So J is, Q, and it was something. One formula that we did. Then it had one import. I told you about this. Just I think this much hint is enough. Something. I think you should remember the formula. Okay, and the answer hint is that, you know, this was lecture number 3. The next lecture, it will be multiple or next lecture, or it could be something like that. Post the answer below in the comment section, and then I'll feel that we were completely successful in learning this topic. This was important topic, and this is being asked repeatedly, like in 2010 and 14, and this question was for 2 marks because they think that this is a kind of a difficult problem. So if you're able to solve this problem, then you should be happy and assured that you are going in a right direction with EDC. Well, that's all for this lecture. See you in the next one.